Okay, so we will talk about nonlinear dimension reduction for visualization today. So after multiple lectures on the clustering of cells, now we will talk about the next step. That is, how do we visualize the cells and the clusters in 2D, in 2 dimensions? Previously, we performed linear dimension reduction using PCA. And the purpose for that step is that we want to first reduce the dimensions. Instead, we work with 20 to 50, a number in the middle, or it's 10 in the tutorial, the number of PCs for further step. So for that step, what we hope is that the lower dimension still preserve meaningful variation. So what we variation is the one we think as likely biological. So here, the underlying assumption is that we don't think the biological variation needs so many dimensions, and we hope that the PCs are enough. But of course, that's an assumption. So then in the PC space, what's in Surat is that we use the Euclidean distances among cells in the PC space to define a neighbor graph, right? Nearest neighbor graph. We start from K nearest neighbor graph, then we convert that to the shared nearest neighbor graph, which is the Jacker index for the edge weights. So given that graph, then we use a graph-based clustering. And the default is the Louvain clustering. You can also choose the Leiden clustering. In the last lecture, we introduced Leiden, and we said that Leiden is a modified version of modified Louvain by adding a refinement step to make sure that the communities stay connected. Okay, so we're basically there. So basically now, after so many steps, every cell has a cluster label. Then the question is, how do we show our data? If we want to publish the results, how do we show the cells, a single cells? So we know that our human eyes can only see up to 3 dimensions. If it's more than that, we cannot see or understand it. So for papers, right, everything on a paper is 2-dimensional. So for UMAP and TSNE, there are 2 popular methods for giving us the 2-dimensional visualization of cells. This is what's said in Surat. So let me bring up the laser. Surat offers several nonlinear dimension reduction techniques. Some people say dimensional reduction. Some people say dimension reduction. So I use dimension reduction techniques such as TSNE and UMAP to visualize and explore these data sets. The goal of these algorithms is to learn underlying structure in the data set in order to place similar cells together in low-dimensional space. Therefore, cells that are grouped together within graph-based clusters from the previous step determined how above should co-localize on these dimension reduction plots. One thing I want to point out is that both TSNE and UMAP and the graph-based clustering rely on the Euclidean distances of cells in the PC space, because the graph is based on that distance, and also that Euclidean distance will be input into TSNE and UMAP. So what I'm trying to say here is that when you do this nonlinear 2-dimensional dimension reduction, your input is not the cell, the original genes, the highly variable genes. Instead, you are inputting the PC data. You are inputting the piece on cell by PC matrix into here. So basically, they take the same input graph construction step. Then it's not surprising that the clusters on a TSNE or UMAP would agree better with the clusters from a graph-based clustering algorithm than some non-graph-based clustering algorithm. So that's just something for your information. So just quickly show you, this is what it looks like. Here, the colors represent cluster labels from the clustering algorithm. And this is the UMAP 2 dimensions. Every dot is a cell. So many people will look at this and say, oh, UMAP is doing a very good job because the cell clusters are, each cluster is indeed together. And what I'm trying to say that this is actually inherent to the algorithm design. They're trying to show the same graph, basically. So therefore, it's not surprising that they agree with each other. But this shouldn't be used as an orthogonal confirmation since they start from the same graph. This is just for your information. While we and others have routinely found 2D visualization techniques like T-SNE and UMAP to be valuable tools for exploring data sets, all visualization techniques have limitations and cannot fully represent the complexity of the underlying data. In particular, these methods aim to preserve local distances in the dataset, ensuring that cells with very similar gene expression profiles co-localize, but often do not preserve more global relationships. We encourage users to leverage techniques like UMAP for visualization, but to avoid drawing biological conclusions solely on the basis of visualization techniques. So this is like a disclaimer placed by the authors of SURAT, just to say that we should just use them for visualization instead of drawing biological conclusions. For example, we cannot say, oh, this green cluster is very far away from them. And we cannot say, okay, this blue one and the orange one are not so distinguishable. So these are the things we should be cautious about, because it's possible once you change, UMAP has two major tuning parameters or hyperparameters I will introduce later. It's possible that you change these two parameters, then the separation of clusters will be different. So therefore, whether they're separated or they're not so well separated, that's not a conclusion. You can just use UMAP to tell you. Okay, but in SURAT, it's very easy to run it. The good thing about SURAT is that it's object-based. So once you have the PBMC object, you just use it as input into different functions. Now we just run UMAP on PBMC. What will be output here? You save it as PBMC. So therefore, PBMC object, data object will have an additional slot about to contain the UMAP coordinates. That's what you get out of it. And this names 1 to 10, what does it mean? I'll introduce it in two slides. And then this is like a built-in plotting function in SURAT. That is, if you have run UMAP, then there is a slot called UMAP in this object. Then you can directly call the slot using the reduction function to specify, okay, you're calling UMAP instead of calling T-SNE, because you can possibly save multiple reduction results in the same object under different names. Then it will be plotted by dimplot. So this is the output of dimplot, which will automatically give you the colors. And because these cell type labels are also, cell cluster labels are also saved in PBMC. Okay, and here is something you can specify names. Basically, if you set label to true, or you can basically just here you're showing, so basically for this one, you're showing the cluster index, but what you can do is that you can change them to your cell type names if you have a good way to assign names to the clusters. This is the UMAP function. There are two key hyperparameters I want to first talk about, n.neighbors, min.dist. So these will appear in a later introduction. We will give you about UMAP. N.neighbors determines the number of neighboring points used in local approximation of manifold structure. So this is like a term manifold. I don't know how many of you have heard about, and we'll introduce it on the next slide. Manifold structure. Larger values will result in more global structure being preserved at the loss of detailed local structure. In general, this parameter should often be in the range of 5 to 50. Min.dist. This controls how tightly the embedding is allowed to compress points together. Is allowed to compress. Larger values ensure embedded points are more evenly distributed, while smaller values allow the algorithm to optimize more accurately with regard to local structure. Sensible values are in the range 0.001 to 0.5. So you can see these two parameters will jointly determine what this UMAP plot looks like, and it's your choice. Okay, and speaking about this DIM, this one, previous DIM 1 to 10, mentions to use as input features used only if features is null. So there's another argument, features. The default is null. So you know in R, if you don't specify an argument, the default will be used. So feature default is null, so you will use this. And then here the reduction means which dimension reduction, PCA or ICA. Should I give you both options to use for the UMAP input, default PCA. So if this PCA and if this features is null, then the DIMS 1 to 10 means that you are using the top 10 PC. You're using top 10 PCs as the input into your UMAP, just like what we use for the top 10 PC for the graph construction. But just a side information, if you set these features to some, how to say, if you set the features to a vector, categorical, character vector, then you can run UMAP on the subset of features instead of running on a set of reduced dimension. So this means that you can say input features here as the gene names. Then if you do that, then UMAP will just be run on the genes you include here instead of using PCA. So that's something for your information, but we rarely use that unless your data is originally low dimensional. For example, there is something called site-seq, which measures single cell RNA-seq data together with the cell surface protein. And so RNA-seq and cell surface protein. And for the cell surface protein part, you only have like 20-something proteins. So that dimension is not that big. You could potentially just start from there instead of doing PCA. Okay, so now we will introduce I will say 5 actually, nonlinear dimension reduction method, starting from this ISOMAP paper. So this paper was actually published in the year 2000 in the journal Science. So it's very rare to have an algorithm published in Science, but this one was, meaning that at that time, it was very, very revolutionary for data visualization. And if you remember, we mentioned about non-negative matrix factorization. That was published in 1999 in Nature. So that was the time when data became, more widely available and data visualization became necessary. So I think that's the reason. So non-negative matrix factorization, NMF, is a dimension reduction technique that's still linear. It's based on matrix factorization. But ISOMAP is nonlinear. What do we mean by nonlinear, right? So if you also recall, we talked about MDS in a previous lecture. It is a way to preserve the pairwise distances in the low dimension. And if your distance, the only input it takes is the pairwise distances of your data points. If the distances are Euclidean distances in the high dimensional space, then MDS has this equivalence to a PCA, right? So that's something we talk about. And in ISOMAP, what it does is that your input is no longer the Euclidean distance in the high dimensional space, but the geodesic distance in the high dimensional space. What does geodesic distance mean? It's a concept together with manifold. So we'll introduce both of them. So this is the paper, and let's first look at the abstract. So let me see. I'll start from here. An approach to solving dimensionality reduction problems that uses easily measure local metric information to learn the underlying global geometry of a data set. Unlike classical techniques such as PCA and MDS, our approach is capable of discovering the nonlinear degrees of freedom that underlie complex natural observations, such as human handwriting or images of a face under different viewing conditions. In contrast to previous algorithms for nonlinear dimensionality reduction, ours efficiently computes a globally optimal solution. And for an important class of data manifolds, it's guaranteed to converge asymptotically to the true structure. Okay, so this is just the abstract. But now let me try to talk about as a review of PCA and MDS, which we covered. So they are simple to implement, efficiently computable, and guaranteed to discover the true structure of data lying on or near a linear subspace of the high dimensional input space. So just give you visualization, a linear subspace in a 3D space could be like a plane or it could be a line. right? If it's two-dimensional linear subspace, then it's a plane. If it's one-dimensional, it's a line. PCA finds a low-dimensional embedding of the data points that best preserves their variance as measured in the high-dimensional input space. Classical MDS, which we introduced, finds an embedding that preserves the interpoint distances equivalent to PCA when those distances are Euclidean. However, many datasets contain essential nonlinear structures that are invisible to PCA or MDS. For example, both methods fail to detect the true degrees of freedom of the phase dataset. This is in that science paper. So let me use this Swiss roll data to introduce the manifold. This is a classical example people use to introduce what does a manifold mean. So essentially, here you can imagine the data points are sampled from a Swiss two arbitrary points, which are circled here on a nonlinear manifold. This is called nonlinear manifold because in the linear space, you can just intuitively see the structure is not straight, right? It's not linear like a plane, but it's like rolling. Their Euclidean distance, the dashed line, may not accurately reflect their intrinsic similarity. If we believe that this Swiss roll is the true structure, then these 2 points distance shouldn't be defined by the Euclidean. But what we should do instead is to follow this structure and find the shortest path within the structure. That's the geodesic distance. Okay, as measured by geodesic distance along the low dimensional manifold, this is the length of the solid curve. That gives you the intuition. Then what's the definition of a nonlinear manifold then? It is a topological space that locally resembles Euclidean space but may have a more complex global structure. Unlike a linear manifold, which is flat, a nonlinear manifold can be curved or twisted in various ways. Then the geodesic distance between 2 points on a manifold is the shortest path between them that lies entirely on the manifold. It generalizes the concept of straight line distance to curved space. All right, this is also from the science paper about if we use this graph-based approach to approximate the geodesic distance, what do we do? So this is basically in the isomap algorithm. So let me just read the text. The first step determines which points are neighbors on the manifold. So what this graph tries to do is that by connecting every point to 7 nearest neighbors, and here we have a total of 1,000 points. So basically we have 1,000 dots here. We connect every point to the closest k neighbors. K is 7 in Euclidean distance. Then with this connection, you see that we are not connecting things that are not supposed to be together in the manifold because we're just connecting no neighbors. And you see this graph mimics the shape of the manifold already. Then if this is a good graph and you just need to find the distance of 2 points by finding their shortest path in the graph. That's it. So by shortest path, that means I have to go from one node to one node to one node, one node, and until I reach this node. And I add up the weights of the edges that connect them. That's the shortest path. Okay. The first step determines which points are neighbors on the manifold M based on the distances dx, ij. X stands for the high dimensional space, and ij are the ijth data points, and d is the Euclidean distance in the high dimensional space in the input space S. 2 simple methods are to connect each point to all points with some fixed radius epsilon. You can have the epsilon neighborhood for each point and connect that to the points, or to all of its k nearest neighbors. These neighborhood relations are represented as a weighted graph G over the data points with edges of weight dxij between neighboring points. This is what we see, the graph. Just for your information, for all the methods that are referred to as manifold learning, they almost all have this graph connection step. So therefore, you are no longer using the Euclidean distance. From now on, you are using the graph. Okay. The neighborhood graph constructed in step 1 of the isomap allows an approximation radians to the true geodesic path to be computed efficiently in step 2 as the shortest path in G. In its second step, isomap estimates the geodesic distances. M stands for the manifold, D and Ij between all pairs of points on the manifold M by computing their shortest path distances, dgij. So this is based on the graph G. In the graph G, one simple algorithm for finding the shortest path is given in table 1. There's an algorithm. So basically, we're using this dgij to approximate dmij because we don't observe the manifold. We're trying to infer the manifold. The third step and final step applies classical MDS to the matrix of graph distances. So once you get the graph distances of all pairs, you input that distance matrix into classical MDS, and then you get a visualization like this. So you see that here the dots are the 1000 dots, but we are visualizing them as is. And here we want to see that the Euclidean distance between 2 points mimics the geodesic distance in the manifold. That's what we do. So finally, we will visualize this instead of the Swiss roll, because here we can still see the Swiss roll since it's just 3-dimensional. If it's more than 3-dimensional, there's no way to plot it, right? But this 2-dimensional visualization is always possible to visualize. Okay. All right. So here, when we say D-dimensional Euclidean space, we mean 2-dimensional. That best preserves the manifold's estimated intrinsic geometry. So what we are drawing here is that this blue line is now the straight line in this isomap 2D space. And we want to use it to say, okay, this is the Euclidean distance in the 2D space. And it should preserve the geodesic distance in the input space. And what we're also showing here is the shortest path. This is the shortest path we obtain in the graph. Right? How do we connect the nodes together? So we're connecting the same nodes in the path. So what we're trying to see here is that they are pretty close. And by having them pretty close, it means that the classical MDS is doing a reasonable job, right? It preserves this red distance, the length of the red curve as the Euclidean space distance. Okay, any questions about this isomap idea? It's very easy to understand if you understand classical MDS. It adds to it by changing the input from Euclidean distances, which actually is equivalent to PCA, to geodesic distances. That's it. Okay. Here is what's the detail in the text. The final step applies classical MDS to the matrix of graph distances, DG matrix, where the entries are the graph distance between nodes I and J. Constructing an embedding of the data in a D-dimensional Euclidean space Y that best preserves the manifold's estimated intrinsic geometry. The coordinate vectors yi for points in Y are chosen to minimize. This is just talking about MDS. How do we find y1 to yn as the n 2-dimensional embeddings? For points in Y are chosen to minimize this cost function. Okay, so cost function is actually used a lot throughout these techniques, and it's actually the same thing as people talk about loss function, something we want to minimize. So essentially, this tau is some operator, which we'll introduce later. Operator is just a mathematical concept as a transformation. And dy is the Euclidean distance in the Y space, in the low-dimensional space. And we'll try to find y1 to yn so that we can get a dy. So y1 to yn is the solution we are seeking. And we seek the solution to minimize this, where dy denotes the matrix of Euclidean distances in the low-dimensional space. So here's just the introduction of what we mean by this distance of 2 matrices. This is like just give you one information. This is an n by n matrix, and this is another n by n matrix. And we measure their distances. We use the so-called L2 matrix norm, which is very similar to Euclidean distance. Yeah, we take the element entry-wise difference, we square them, and we sum them, and then we take the square root. This tau operator converts a distance matrix to inner product. This is what we introduced in MDS, if you recall. We call this gram matrix. So we convert a distance matrix to a gram matrix, which can be considered as X transpose. They have one-to-one relationships. Once we get that X transpose, we try to find X by eigen decomposition. And same here. So that's called the tau operator, which uniquely characterizes the geometry of the data in a form that supports efficient optimization. The global optimum of this one is achieved by setting the coordinates yi to the top d eigenvectors of the matrix tau dg. This is exactly what we do in classical MDS. So you input dg, the graph distance matrix, you convert it to a gram matrix by the tau operator, then you do eigen decomposition. As with PCA or MDS, the true dimensionality of the data can be estimated from the decreasing error as the dimensionality of Y increases. We also can have something like an elbow plot, but we're not showing here because I think in practical use, you only can do D equals 2 or 3, right? Honestly, you cannot go beyond that. Otherwise, you violate the purpose of visualization. For the Swiss roll, where classical methods fail, the residual variance of isomorph correctly bottoms at D equals 2. So basically, it identifies that the manifold is essentially two-dimensional. Okay, this is the isomap algorithm. 3 steps. Let's just reiterate it so that you can have this review. First step, construct neighborhood graph. Define the group points ij if, as measured by dxij, in this X space, input space, they are closer than epsilon, which is called epsilon isomap by the epsilon neighborhood to connect the graph, connect nodes into edges. Or if I is one of the k nearest neighbors of j, this is called k isomap. So 2 versions for the graph construction. Set edge length equal to the Euclidean distance. Given this graph, second step, compute shortest path. Initialize dgij to be dxij if ij are linked by an edge, if they are connected in the graph. Otherwise, set dgij to be infinity. If they're not connected, then there's no way to know how close they should be. But we will update this. Then for each value of k from 1 to m. So please know that this k is just an index that goes through our data points. It's not related to this k nearest neighbor. So k goes from 1 to big N. N is the number of data points. In turn, replace all entries dgij by the minimum 2 values. Their graph distance from the previous iteration, or their sum of distances by connecting to a third node, dik plus dkj. That's just k is the middle node. So we do this iteratively until we cannot change the values. So you can imagine if this ij are points like this, their initial dgij will be infinity. They're not connected. But as we update, we'll gradually find middle nodes to connect them. That's what I mean. Okay. So because this infinity is always bigger than this possible second term. So that's why we will get the minimum instead of getting the infinity. Okay, the matrix of final values will contain the shortest path distance between all pairs of points in G. And this is from a previous literature. So these are citation numbers, reference numbers. Final step, construct D-dimensional embedding. And this is what the classical MDS is. So basically we input a geodesic distance matrix into MDS and we get the embedding. So I'll skip this technical detail because for this, you need to understand classical MDS to understand this description. So let's quickly show some applications. This is very interesting. Applying this to 3D face images, you can see that this is one shortest path connecting this face to this face. So, and we find the and the images along the path. We see that it's just how to say MDS PCA finds such path. So basically, in this case, the reasonable distance between this face and this face should be the length of this path. instead of Euclidean distances between the pixel images. That's what I mean. Okay. And another very interesting application. See, these are hand images. So again, connecting this one to this one, you can grab and open up, and similarly have the hand change the orientation. So you see those changes along the path. And finally, this is a handwritten image. So in the early days of computer vision, this data set has been widely used by handwritten digits. And you see that in this path, we gradually change the shape from left to right, similarly here. So I think at least these changes are reasonable to our human eyes. So that's why, something I want to say about computer vision as opposed to our bioinformatics is that computer vision has a very big advantage. That is, the data is intuitive. Our human eyes can tell us easily whether the algorithm is reasonable or not. But such level of intuition is lacking in bioinformatics because we know so little biology. That's just the reality. And that's why we generate those data to find new biology. And here we're not trying to find any new science. We just want to have a tool to work with those data, just like our human mind. And that's a fundamental difference. I hope you can keep this in mind. We don't have that many intuition. So therefore, I think for bioinformatics data, given that what is signal, what is noise is not clear, I feel like it's necessary that when we describe our algorithm or write our papers, we make it clear. At least people know, okay, this is our assumption and this is the data. All right. Interestingly, on the same issue of science, there is another paper called LLE. So they're back to back on the same issue of science. So you may wonder, why do we do nonlinear dimension reduction method? So the key difference here is that this one focuses on local linear embedding using a completely different approach, which is very interesting. So the assumption, let me quickly go to the paper. So this is the LLE output, which is also the Swiss roll data. You see, they both use the Swiss roll data. And here they're trying to see that, okay, by local linear embedding, for this point, it also considers the neighbors in the Euclidean space. And it tries to say, okay, this relationship is trustworthy. Basically, see, what we take from this nonlinear dimension reduction is that even though globally the Euclidean distances are not meaningful, because we may connect two points far away in the manifold with a short Euclidean distance. So globally, Euclidean distance is not reasonable, but locally, Euclidean distance is still reasonable. So that's why in the graph construction, we're still using the Euclidean distance, but only locally. That's the key thing to keep in mind. So here, it tries to say that, okay, for this neighborhood in the original input space, the points here stay as in one neighborhood in the LLE, in this black circle. So that it tries to justify it's reasonable. And what it does is that for this point, it tries to find some weights of the neighbors to explain this point, like a prediction problem, like a linear regression prediction problem. So that's quite local linear embedding. And then it fixed the weights, try to find the low dimensional embeddings yi's, so that given the same set of weights and given the yi's, we can reconstruct this point in the low dimension space. So it's a very interesting idea, using a high dimensional input space to find weights, and then using the low dimensional embedding to find embeddings by fixing the weights. Okay, so maybe we can quickly go through the paper here. So this is what the author said. They take a different approach called LLE that eliminates the need to estimate pairwise distances between widely separate data points. So it doesn't have this geodesic distance step. Unlike previous methods, LLE recovers global nonlinear structure from locally linear fits. Assumption is that even though the Swiss roll is globally nonlinear, but for local neighborhood in calculus, we can approximate a curve locally by a line. Same idea here. The LLE algorithm, summarized in figure 2, is based on simple geometric intuition. Suppose the data consists of n real value vectors xi, the data points, each with dimensionality big D, sample from some underlying manifold, provided there is sufficient data such that the manifold is well sampled. Basically, you need to make sure that they are dense, so you have the shape of the manifold. We expect each data point and its neighbors to lie on or close to a locally linear patch of the manifold. We characterize the local geometry of these patches by linear coefficients that reconstruct each data point from its neighbors. This is it. So we're trying to take the neighbors J of I, so to find the weights Wij, which are the linear weights or coefficients to construct Xi from these Xj's. Reconstruction errors are measured by the cost function. This is the objective function, cost function for linear regression, which adds up the square distances between all the data points and their reconstructions. The weights Wij summarize the contribution of the jth data point to the ith reconstruction. To compute the weights Wii and Ij, sorry, I think it's just truncated. Ij, we minimize the cost function subject to two constraints. This is a constraint linear regression. First, only the neighbors have Wij non-zero. Other non-neighbors have Wij zero, okay? Second, we constrain the weights to sum up to 1. All right, so once we have the weights, then we solve another optimization problem. That is want to find the Yi and Yj. So each Y for one data point. So here, what we do is that here we fix the weights from the previous step while optimizing the coordinates Yi in the 2D space. The embedding cost, which is here, defines the quadratic form in the vectors Wi. Subject to constraints that take the problem well posed, it can be minimized by solving a sparse n by n eigenvalue problem. Again, eigenvalue problem, whose bottom D non-zero eigenvectors provide an ordered set of orthogonal coordinates centered on the origin. This is something good to know. So, for this problem, it turned out to be finding the bottom D non-zero eigenvectors instead of top D. All right, so I feel like this message can give you some intuition or some message that linear algebra is very important for machine learning data science, because you're basically doing linear algebra. And even though it's like non-linear for the manifold, but when you solve this local linear problem, it's linear algebra. So without going to further technical detail, this figure illustrates the algorithm. So this is supposed to be your input space. You connect, again, you identify the neighbors. So both algorithms have this neighbor identification step based on the Euclidean distances in the high dimensional input space. Given the neighbors, you try to find the weight for each neighbor to predict Xi. And given the weights, you try to find the embeddings, Ys, so that you can keep the same weights and minimize the reconstruction. So you can use these neighbors with those weights to predict or reconstruct each I. That's it. Okay, so this is the output of LLE. So still they use the phase images. And what you can see here is because you don't have a graph for the manifold to represent the manifold, or you don't have the geodesic distance for the shortest path, what you have instead is that it's just an interpretation of whether the low dimension embeddings are reasonable. What the authors did is that they tried to follow this path and put the phase images along it. And basically the same phase images along the top diagonal path is placed in the bottom. So what they try to show is that you still have this phase change gradually, like this person gradually smiles. So that's what it tries to show. All right, so now let's compare these two early methods published in Science 2000, ISOMAP versus LLE. So their goals are different. ISOMAP tried to preserve global geometric structure. LLE tried to preserve local geometric structure. One is global, one is local, because this one doesn't even have the global geodesic distance. For graph construction, ISOMAP can construct neighborhood graph using the K nearest neighbor, K ISOMAP, or fixed radius epsilon ISOMAP, While in LLE, the default is to use K nearest neighbors because you have to specify the neighbors, right, to do get the weights. Okay, and distance measure, geodesic distance, which is approximated by defined as the shortest path on the graph for isomap, but there's no direct usage of distances in the LLE. Embedding technique, the isomap uses MDS with the geodesic distance matrix. LLE minimizes the reconstruction errors of local neighborhoods. Okay, that's just how we find the YIs. Advantages, isomap captures global data structure, good for data with significant curvature. While LLE captures local data structure well, it's effective for data with locally linear structure. So depending on what the data is like. Disadvantages, geodesic distance can be computation intensive for large data set, which is actually step 2. When you try to find the geodesic distance, because just quickly go back, in this step, you have to go through all data points. And you can imagine if n is 1 million, you have to take 1 million steps, right? If it's 1,000, then 1,000 steps. So it's basically that scale. And disadvantages, it can be computation intensive. And for LLE, it can be sensitive to noise and outliers. The reason is that we know this linear regression formulation will be sensitive to outliers because that if you have a neighbor which is weird, then the weights will be weird. Okay, so that's the 2 early methods. Now we have more recent methods used in Surat. So finally, we'll do a comparison between these 2 groups of methods and try to explain why these methods are more popular for Surat or more used in Surat. So this is a very nice cartoon from this very well-written blog. So this blog basically says that, okay, there are 3, if you trace it back. So the earlier one is this one, called SNE, stochastic neighbor embedding. Then it changed to TSNE. TSNE is visualizing data using TSNE. So I remember TSNE is about like 2008 paper. SNE is probably 2006 paper or 2005 paper. Then UMAP. UMAP is a very recent paper, like 2018, 2019. So this is the change. TSNE goes to TSNE changed to TSNE, and finally UMAP is modified from TSNE. Okay, so you can see that this is also kind of universal for method development. A method is usually developed on top of existing method to fix some limitations and to gain some advantages. But what this says is that if you are a method developer, then knowing the literature, knowing what are the existing methods there is necessary. Otherwise, you might be reinventing the wheel, right? Doing something people have already done. All right. The lesson is intended to be this one. This blog, I strongly recommend, is intended to be a digestible guide, maybe a first step before reading the complete papers, the 3 papers. For time-strapped machine learning practitioners to help understand the underlying logic and evolution from SNE to TSNE to UMAP. So especially the UMAP paper is very difficult to read. It's written as a mathematical paper. And the interesting thing is that the original UMAP paper is still unpublished. It's just an archive paper. But later somebody applied it. I think soon after it was posted on archive, some people applied it to single cell data and made that paper to Nature Biotechnology. I think that's when this UMAP became popular. But the original math heavy paper remains unpublished. Okay. And I think some people are still trying to understand the UMAP paper to see whether the theory is really right or not. Yeah, just for information. But sometimes you see application can go first before the theory is confirmed. So this is from the blog post saying that if you want to embed images like those traffic signs, what machine learning does is you first encode each image by an embedding. So here you can, this is like manual encoding. Sign, stop, English, symbol, octagon. So you encode them, then you generate in 5 vector 2D space. in the hope that similar traffic signs are grouped together. That's the illustration. Dimension reduction plays an important role in data science as a fundamental technique in both visualization and pre-processing for machine learning. Dimension reduction methods map high-dimensional data in X, X1 to Xn, into lower dimensional data Y, Y1 to Ym, with big M being the number of data points. So this is the same notation as used in isomap, right? So big M for number of data points, X for input space, Y for the 2D embedding. In essence, computing embeddings is a form of dimension reduction. When working with unstructured data, like the traffic signs, the input space can contain images of size like width, height, channels, or tokenized language. This is actually what's behind the large language model, the tokens, audio signals, etc. For instance, let the input space be composed of images with resolution 1024 by 1024. In this case, the input dimensionality is larger than 1 million. Let's assume you use a model such as ReNet or EfficientNet and extract embeddings with 1,000 dimensions. So this is like the computer vision neural network to convert an image into 1,000 dimensional vectors. In this case, your output space dimensionality is 1,000, 3 orders of magnitude lower. This transformation turns the very large, often sparse input vectors into smaller, dense feature vectors or embeddings. Here, we refer to the subspace as the feature space or embedding space. Okay, so we want to get embeddings. There are extensive amount of dimension reduction techniques. They can be grouped into 3 categories: feature selection, matrix factorization, and neighbor graphs. So the linear dimension reduction methods we covered previously belong to matrix factorization, right? And including PCA, GLM PCA, NMF, PNMF. But what we introduced as the geodesic distance, the one isomap, is neighbor graph. You start with a neighbor graph. We'll focus on the latter category, neighbor graph, which includes SNE, T-SNE, UMAP. The 3 algorithms operate roughly in the same way. Compute high-dimensional probabilities P, compute low-dimensional probabilities Q, calculate the difference between the probabilities by a given cost function between P and Q, minimize the cost function. Let's start with SNE. SNE, first step, the earliest one, it calculates high-dimensional probabilities. So what it does is that we start by computing the probability Pj given I, that the data point I would pick another point J as its neighbor. Just defined in this way. So we take the Euclidean distances between I and J, we square it, take the negative sign, put it into exponential function. This is very similar to the Gaussian density or Gaussian kernel. You convert the distance to a Gaussian density value. So the larger the distance, the smaller the value. The smaller the distance, the larger the value, but the value is always positive. And you normalize the value by summing over all the other J's, right? Excluding I. You sum up over other neighbors so that you can make sure this Pj given I, if you sum over J, will be equal to 1 because of the normalization. All right, this is where Dj given I represents the dissimilarity between high dimensional points xi, xj. It's defined as the scaled Euclidean distance, xi minus xj, scaled by 2 times sigma I squared. So if you're familiar with the Gaussian density, that's what it is, right? So we have the square distance divided by 2 times the variance. The mathematical intuition is that given 2 points x, xj, the farther away they are, the higher their distance dj given I, the higher their dissimilarity, and the lower the probability that they will consider each other neighbors. The key concept here is the further away 2 embeddings are in the space, x, xj, further away, the more dissimilar they are. Note that the dissimilarities are not symmetric due to the parameter sigma I. So you see, when you calculate Pj given I, here you involve 2 sigma I squared. When you calculate di given j, it's like 2 sigma j squared. In practice,
the user said the effective number of local neighborhoods is so-called perplexity. Perplexity is a hyperparameter in t-SNE. Once the perplexity k is chosen, the algorithm finds sigma I by a binary search to make the entropy of the distribution over neighbors equal to log 2 of k. K is what? K is your perplexity. That's what you said. So essentially what it tries to do is that given you set k to some number, say 20 or 50, you try to find the corresponding sigma I value to satisfy this equation, because pj given I depends on sigma I squared. Okay, and the concept here is from information theory. So this is like a Shannon entropy formula measured in bits. From the previous equation, we obtain this just the same thing, but we solve for k. K has this form. So by tuning sigma I, we tune the right-hand side until it matches the perplexity k set by the user. You set the k, and you find the corresponding sigma I. The higher the effective number of local neighborhoods, the perplexity, the higher sigma I, and the wider the Gaussian function used in the similarities. So what it says is that the larger sigma I, the wider the Gaussian density is, then you will cover more neighbors. More neighbors will be considered as neighbors instead of having very narrow Gaussian where you only pick the closest neighbors. So that will determine the neighborhood size. So that's why perplexity k is crucial. The larger the perplexity, more points are pulled together. While if you have perplexity very small, you may have some small clusters in your t-SNE plot, which we'll talk about. The mathematical intuition is that the higher the perplexity, the more likely it is to consider points that are far away as neighbors. One question may arise. If the perplexity is user determined, how do we know which one is correct, right? Always the question for hyperparameters. This is where our science. The choice of perplexity is crucial for space that we can visualize using a scatter plot, 2D space. If we pick too low of a perplexity, clusters of data points that we expect to be together, given their similarity, will not appear together, and we will see subclusters instead. That's what Jessa said. So you will see many subclusters if the perplexity is low. On the other hand, if we pick a perplexity too large for our data set, we will not see correct clustering, since points from other clusters will be considered neighbors. Okay, there isn't a definite all good value for the perplexity. However, there are good rules of thumb. All right, so there are some empirical rules which I will not talk about, but we will talk about that at the end. Then given the P's calculate Pj given I calculated in step 1. Step 2, you calculate low dimensional probabilities. Now that we have high dimensional probabilities, we move on to calculate the low dimensional ones, which depend on where the data points are mapped in the low dimensional space, the 2D. Fortunately, these are easier to compute. SNE also uses Gaussian neighborhoods, but with fixed variance. So there's no sigma I, no perplexity in the low dimensional probability. You just take the low dimensional Euclidean distance, do this Gaussian kernel, and that's your Qj given I. But please bear in mind, since Yi and Yj are what we try to find, this is just a conceptual thing. We don't know how to calculate it yet. So we're trying to use this to make it close to the Pj given I to find Yi and Yj. So step 3 is that we need a way to measure the difference between P and Q. And the cost function here is designed based on the so-called callback-Laborer divergence, short as K-Val divergence. All right, what does it mean? If the points Yi are placed correctly in the low dimensional space, the conditional probabilities P and Q will be very similar. To measure the mismatch between both probabilities, SNE uses the KL divergence as a loss function for each point. Each point in both high and low dimensional space has a conditional probability to call another point its neighbor. Hence, we have as many loss functions as we have data points. You have one loss function, KL divergence for each I. Then you sum up over I. Hence, we have as many loss functions as we have data points. We define the cost function as the sum of the KL divergences over all data points. That's the C. Then the Steen algorithm starts by placing all the yi in random locations very close to the origin. And then it's trained minimizing the cost function C using gradient descent. Details about the differentiation of the cost function is beyond the scope of this course. So later you're going to take differentiation or partial derivatives in C against the yi, against each yi. And then you try to use the gradient to help you minimize the C. So this algorithm is known as gradient descent, which is something very important in machine learning. So here, C is basically a function of y1 to ym, what we try to find. And each yi is two-dimensional. What we're trying to do is that we're trying to get a gradient in each of the, we're kind of doing the block gradient, honestly, because each yi is two-dimensional. So we're going to find what direction in this yi change can make this cost function smaller. Then we go in that direction. So gradually we iterate through y1 to ym to make the C smaller. And then we go another round. So that's the gradient descent algorithm. So KL divergence is the measure. Let me just quickly say what this is, because you might not be familiar with this one. KL divergence. It's a measure of how one probability distribution diverges from a second reference probability distribution. It is often used in statistics and machine learning to measure the difference between two distributions. Here is an intuitive explanation. Suppose you have two probability distributions. P is the true distribution and Q is the approximate distribution. Same as here. P is the high dimensional distribution we try to preserve. Q is the low dimensional distribution we try to find to approximate the P. And we use KL divergence to measure the information loss, which quantifies the amount of information loss when Q is used to approximate P. So this is the form, which is exactly what we do. So, it's not symmetric. So you make sure that when you use the double vertical bar, true distribution is written first, then Q is behind the bar. You cannot change the order because it's not symmetric. You see, it's not like you can swap P and Q. So essentially, it can be considered as the expectation of this log density ratio under the true density P. That's what exactly it is. It's a log ratio, and you take the expectation with respect to the true density P. Okay, and it's always non-negative. This is very important to know. It cannot be negative. And this can be proved by some inequality. You can actually show that. All right, so this is the KL divergence introduction. What's interesting for us is this very nice intuition. So we're plotting the KL divergence for a value of P and Q, and the height is the value. P is one axis, Q is one axis. So let's see what the authors wrote. If two points are close together in the high dimensional space, their dissimilarities are low, and the probability P should be high by our definition of P. So if they're, like say Euclidean distance is 0, high dimensional, then the P should be equal to 1 by definition. Then if they were, so when P equals 1, we're in this end. Okay, this is where P equals 1. Look at this curve right here. Then if we were mapped far away, if the 2 points are mapped far away in the low dimensional space, then Q should be 0. Okay, then in this scenario, P is 1, Q is 0, you are right here. Then in this scenario, we can see the loss function takes very high values. It's not good. It's not ideal. So you see, when P equals 1, at this curve, I'm trying to draw it, we should minimize it and go here. And that will give us Q equals 1, which means that we will also push the 2 points together. in the low dimension space. That's good. But on this end, we have a problem. On the other hand, it's unclear. Q could be close to 0. Q could be large, right? So therefore, for 2 points far away from each other, their low then may be low. So it could be small. So that's why it's not good. So this implies that this KL divergence will not preserve small p well as small q in the low dimensional space. That's a problem just because of this end. Okay, I think this is a very good graphical illustration. Then T-SNE. So that's basically SNE. And just to summarize, SNE has two probability vectors, one for each data point I. For each data point I, there's a probability vector as long as the number of data points. We have n probability values, and we calculate them in the pi-dimensional space based on the Euclidean distance and also based on sigma I, the perplexity determine that. In the low dimensional space, we don't have sigma I. We set all the variances to the same, but we use the low dimensional Euclidean distances. So suppose we have P and Q set up in that way, we try to minimize the KL divergence to find the corresponding YI, YJ so that the low dimensional embedding scheme must give me the Q. That's it. Okay, what's T-SNE? So T-SNE tried to solve some problems for SNE. Two things. First, the cost function is difficult to optimize and has a crowding problem. So crowding problem means that you may have data points too crowded in the 2D space to be visually separable. And so it uses the T distribution instead of the Gaussian distribution for the low dimensional probability. That's one change. Another change is that it tried to make the probabilities P, J given I, and I given J symmetric, which is not something the SNE has. These are the two major changes. So this is in T-SNE. What we do is that we take the average of Pj given I and Pi given J and call that Pij. Okay, so then the Pij's will sum up to 1. They are like I and J pair. Instead of Pj given I is that given I look at the J's. So that's why, because these are pairs, we additionally divide an n here to make sure the Pij sum up to 1 instead of sum up to n. That's the reason. That's the first thing to make it symmetric. And just for your information, once you make this symmetry or symmetrization, the cost function becomes easier to optimize. Another thing is this Q. So in the definition Qij in the low dimensional space, it's no longer using a Gaussian density. It uses the T density. So this is the density function of a T distribution where distance square, take the inverse of that. So this is the T density function. And what it does is that the T density function, if you are not familiar with it, check the Wikipedia, and it will show you that it's more heavy-tailed than Gaussian. So by being more heavy-tailed than Gaussian, there is an advantage. That is, you will tend to push data points farther away for the same density value. So what I mean here is, I think that this point here, right here. I'll try to quickly draw things here to give you the intuition. So like this. Let's say that we have this density. This is the Gaussian density, okay? Suppose that we call them the T density. And the T density, both are set at 0, is more heavy-tailed. Okay, so it's a little more heavy-tailed. And what I mean here is that the y-axis is the density value. Okay, so this is the density. Maybe we'll just see P. And so this one is for the P value, or the blue one is for the Q value. I'll just do the same roughly, not exactly. So, and if this x-axis indicates the p thing, okay, so this thing. So what I mean is that even the same density value, you will see that and symmetry of zero. No. The distance we find under the Gaussian density is smaller than the distance we find under the T density because of the polygon. And this bigger density means that using the T distribution in the low dimensional space, you push points farther away. That's it. So for the far away data points, you push them farther away. But for the data points close to zero, you make them very closer. So you are having a more exaggerating effect in your low dimensional space. And making them to push them far away, for far away points to push them far away, actually allows you to have a better separation and less of a problem. So that's just a conclusion based on the T distribution. And that's the reason why this T algorithm uses T distribution instead of Gaussian distribution for the low dimension space. Just try to avoid the crowding problem. The intuition is that since the KO divergence function does not penalize the misplacement in low dimensional space of points that are far away in high dimensional space. You remember we talked about that issue in the KO divergence right here. This one is when the distance is big, P is small, KO divergence doesn't do well. So that's why C uses the T distribution as a fix. We conclude, okay, that the global structure is not well preserved. So that's the same issue with both SNE and T-SNE, just due to the use of KO divergence. But I want to say that T-SNE uses a T distribution to push farther away points far away. So that's kind of like a, how to say, moderate fix. Okay, so finally, I don't think we can finish it, but we will just stop at the UMAP. We say that UMAP has some similarities with both SNE and T-SNE, but it's more complicated. By being more complicated is that it has this additional parameter, rho I. Okay, so what it does is that instead of using probabilities, it directly works with similarities. So there's no normalization step here. You just have this distance and minus rho I over sigma I, negative sign exponential. So kind of similar, but with some subtle differences. Like this is like sigma I instead of 2 sigma I squared. But you can see there's one-to-one monotone relationship between them. And rho I is something you add additionally. You work with similarities and you try to preserve the pairwise similarities in the low dimensional space. It uses the symmetry of J given I, and the symmetry of I given J will be symmetric. Okay, and it's also uses this kind of idea to help determine sigma I, very similar to that perplexity, but the formula is based on its own similarity formula. Right, so the key difference, which I'll come back again, is the use of the cross entropy as the loss function instead of KO divergence. So you see a very sharp change is that when P is close to 1, you have the curve like this, which will give you better optimization for Q being 0. Instead of here, when it's flat, you cannot see where it is. So this just a change of loss function that can make a very big difference. So we'll stop here for today and we will resume, I think, on next Wednesday, because next Monday seems to be a holiday. Yeah, so, but in the meantime, I hope you can further study the materials during the time and then come back with some questions next time. All right, thank you very much. Yeah. Let me try to